Right, our speaker tonight is Charles Monson. Charles is an assistant project coordinator in petroleum geology with the Illinois State Geological Survey. He has a master's degree from the University of Iowa. His research interests include clastic sedimentology and stratigraphy, lower Paleozoic paleontology, history of geology, and meteorite impact craters. His program tonight is the Glasford structure, a marine target impact crater with a possible connection to the Great Ordovician meteorite shower. Charles.
So thank you for the introduction. I'm Charles Monson. I work at the Illinois State Geological Survey, like you said. Subject of my talk today is the Glasford structure in Peoria County. Before I begin, any project like this obviously is not a one-man show. I have quite a few collaborators at a bunch of different institutions who made this work possible. I'm not going to name them all individually, but I'd just like to say thank you to all of them for helping me conceive this project and move it forward. Okay, the structure of my talk today, I'm going to start off with just kind of a few generalized comments about impact structures, and then talk about the Glasford structure specifically, what it is and its history of study. And then I'll go into the recent investigations I've done with my team over the last 5 years or so, kind of bringing the crater into the 21st century, basically. I have a few different versions of this talk that I give to different groups. Some of them have more technical detail than others. Hopefully I'm pitching this one at the right level of detail, but if I'm ever saying either giving not enough detail or too much detail, feel free to let me know. And I'm happy to answer questions as we go through if that seems easiest. Okay, so when most people think of meteorite impact structures on Earth, I imagine they picture something like this, a giant rock hitting what is now the Yucatan Peninsula about 65, 66 million years ago, killing off all the non-avian dinosaurs along with some of their relatives like the pterosaurs and some other things, creating a nuclear winter, et cetera, et cetera. And of course, this the end Cretaceous extinction, which has been tied pretty conclusively to a giant meteor impact, is a fascinating event in Earth history, but it's not the full story of impact cratering on Earth by a long shot. Impact cratering in general has been described as a fundamental process in the solar system, shaping planets and moons. The person who framed it that way was someone who studies impact craters, so he's a little bit partisan on that, but I think a fair case is to be made. The last time I gave this talk, these pictures of Mars are in here, because the last time I gave this talk was the day after Perseverance touched down in Jezero crater on Mars, which of course is the site of an interpreted ancient river delta, a place where they're going to be looking for possible fossilized signs of ancient life, among other things. But when we say it's a fundamental process, we really mean that quite literally. There was a recent study a couple years ago which suggested that large meteor impacts on the primal Earth might have helped initiate plate tectonics. And of course, there's really no more fundamental process on Earth than that, geologically. Okay, so impact craters on Earth. How many are there? It really depends on who you ask, because oftentimes there's a little bit of haggling about exactly which impact structures are proven to be meteor impacts and which are not. And they're discovering new ones all the time. But as of a couple years ago, at least, the last big compendium I saw, an even 200 was a pretty good estimate. I think a couple more have been tacked on since then. 200 impact structures along with 46 ejected deposits. Ejected deposits just being a situation where evidence of impact, little melt blobs spraying out of a crater when it forms, things like that, lots of other possible things are discovered, but can't necessarily be tied to a known crater. The oldest evidence of impact on Earth is a 3.5 billion-year-old layer of impact spherules found in Africa and Australia. So that's one of those ejecta deposits. The most recent crater we know about, if you can call it a crater, is the hole in the ice that the Chelyabinsk meteorite punched on a frozen lake about 8-9 years ago. Now, when I say there's 200 impact structures on Earth, those are the ones that are pretty much accepted by the planetary science communities. There's hundreds of dubious candidates also. Every time somebody finds a vaguely circular structure on Google Earth or out walking in the woods, there's a temptation to say, hey, I found a meteor crater. So the planetary science community has some fairly appropriately stringent criteria for how you can identify something as being a genuine impact crater. And we'll get to that later on in the talk. So here's a map from that same compendium from a few years back, published in Astrobiology, showing the spatial distribution of these things, and also tells you something about the size. Each dot is an impact structure, and the size of the structure, the size of a circle indicates the bigger the circle, the larger the structure. So you can see, Chicxulub there in the Yucatan. You'll notice, of course, that a lot of them are clustered in North America, United States, Canada, Europe, Australia. Some of that could be a real geological signal. Most of it probably is just a question of people looking in the right place with the right equipment. Chances are there's a great many undiscovered meteor craters in these areas. We just haven't found them yet. So that's 200 on Earth, 200 and counting. Of course, the moon is much smaller and there's thousands of large craters on the moon. One estimate I read saw that there's 1 million craters that are larger than a half-mile on the moon. So why only 200 here? Well, as Earth Science Club members, I'm sure you know the answer to that one. Earth is a geologically active planet. When a crater gets formed, there's all kinds of ways that it can relatively quickly get effaced, eroded, buried, just generally removed from view, and in some cases, partially or entirely destroyed. So no doubt there have been no small number of impact craters that we'll never know about because they've been just obliterated by geologic processes. And there are probably many, many more that are buried, that were only partially preserved and are now buried, that are waiting to be discovered. Here's an example. Here's examples of a few of them. An awful lot of these craters, like I said, are largely or entirely buried, or if they are exposed, oftentimes they've been altered quite a bit by nature since they were formed. There are places on Earth you can go and see some pretty good examples, though. The one on the left, the big one, is the Rutherford Dome in South Africa. I think this is at least the oldest, the largest recognized meteor impact structure, and it's one of the oldest ones too. With something like this, because the radius of different kinds of damage is so large, exactly where you kind of draw the line on what's the outside of the crater and therefore what the diameter is, again, kind of depends on who you ask. But I've heard estimates that this one was about 200 miles wide when it was first formed. Then you have things like Barringer crater down there on the lower right, which is less than a mile wide. That's the famous meteor crater in Arizona. You get some kind of weird things too, like in the upper right there, you see Clearwater West and Clearwater East. Those are two lakes in Canada, which are both thought to be meteor craters. You see them right next to each other, and kind of the logical assumption is, oh, maybe there was one bolide that split in two shortly before impact and formed these two craters right next to each other. But a few years back, there was actually a paper published which argued that these were something like a couple 100 million years apart in terms of when they formed, based on dating of some of the material they found inside the craters. And it was just pure coincidence that they formed next to each other like that. Here in the Midwest, we are blessed with quite a few really interesting meteor craters in our fairly near vicinity. Um, the one I'm going to be talking about today, Glasford, is kind of right here in the center of this image. This is not even a complete view. This map is based on a somewhat outdated database. There's a couple in Iowa and Wisconsin, I think, and a few other places that have been discovered fairly recently that aren't even reflected on this map.
And don't forget this plane.
Well, yeah, we're going to get to that. We'll be getting to that. Since I'm originally from Iowa, I worked at the Iowa Geological Survey briefly, and I think I see Ray Anderson on here. Hi, Ray. I'm going to mention a couple of important craters in Iowa first. Manson Impact Crater, Ray knows all about this one. The second largest intact crater in the United States after Chesapeake Bay. Happens to be Cretaceous aged, and for a while it was considered a strong candidate to be the crater that was formed by the impact that killed the dinosaurs. Eventually, it was determined that it was actually a little bit too old for that, but it's still a pretty interesting place. Lots of good work done there. Another one that was very recently discovered that was not on that map is the Decorah crater in Iowa. I had to throw this one in because this is the first meteor crater I worked on. It's kind of just across the border from Illinois and Wisconsin in northeast Iowa, sorry. It's about 3.5 miles wide. It is almost entirely buried under the town of Decorah. And in order to get at it, the Iowa Geological Survey team dammed off a portion of the upper Iowa River with a backhoe, drained it, and then went down and started pulling up big pieces of shale. And the cool thing about this one is this crater actually contained really unusual fossil deposits. The shallow marine conditions inside the crater managed to preserve some things that wouldn't usually get preserved. My favorite part of that field experience was peeling open, like separating pieces of shale and finding these weird tissue paper thin carbonized films in between them, which were shaped like pieces of a giant arthropod, because that's what they were. They were actually cuticle from a giant sea scorpion, a eurypterid. And we found huge numbers of pieces of these things, incredibly fragile. A eurypterid specialist eventually took them all and kind of assembled them and figured out what this thing looked like. It was actually the oldest known eurypterid at that time. But you're here for Illinois, so let's get to Illinois. There's two impact structures in Illinois that we know about. Statistically, based on what we know about the rate of cratering over time, what we think we know at least, there's a pretty decent chance that there's additional buried impact structures in Illinois yet to be discovered. They may or may not ever be found, depending on whether somebody drills a well in the right place or whether they got destroyed by erosion sometime during the Phanerozoic. But one of them that did survive is the Des Plaines disturbance. That's near the town of Des Plaines in the Chicago suburbs area. It's a 5.5 mile wide, 25 square mile area of heavily disturbed rock. I don't think it quite reaches under O'Hare Airport, but it comes, the outer boundaries of the disturbance come very close to O'Hare, which I believe is down here. Not a great deal is known about Des Plaines, actually. There's been only one real paper about it that was maybe at least 30 or 40 years ago, I think. It's buried, and it was pretty heavily affected by erosion and other forces before it was discovered. So we don't know how old it is. Based on the rock that it formed in, the oldest it could be is about 300 million years. The youngest it could be is about 2.5 million years. So we got a pretty big error bar there. Hopefully someday we'll be able to pin a better date on it than that. What we do know about it comes in part from some big construction projects for, I think, channeling water underground, and also some transportation tunnels and things. They drilled through parts of the disturbance, and so they have some core from it based on that. I'm hoping to take a look at that core myself someday, because this is overdue for someone to look at it again. But that's for another day. Today, we're going to talk about Glasford, which is the other known impact structure in Illinois. As I'm sure a lot of you already know, Glasford is a village in Peoria County. It's about 15 kilometers southwest of the Peoria suburbs. Population just over 1,000 last time I checked. So if you drive a little ways northeast of Glasford, kind of towards Peoria, in between Peoria and Glasford, if you go out on Cowser Road, Kingston Mines Road, to where the Glasford impact structure is, this is what you'll see. Flat agricultural land. If you go there now, you'll see cornfields starting to come up. If you look in the right place, like right at the crest of the structure, you'll see some gas storage dome facilities. But, you know, visually, nothing obvious to indicate that anything out of the ordinary geologically ever happened here. I read one newspaper article about it claiming that there's a little bit of a dome, which is just enough to kind of alter the flow of streams in this area. I couldn't see it. I've been there once and it looked dead flat to me. So the whole thing is buried, essentially. So how do we know about it if it's completely buried under farmland? Well, it goes back to the middle of the last century. Basically, a dome at that location was identified by Illinois State Survey geologists just in the course of regular geologic mapping in the late 40s, early 50s. Domes are of interest for economic geology, potentially. Sometimes they have oil accumulations. They can be good places to store natural gas. Sometimes if something like a coal seam is there, the dome brings it a little closer to the surface, makes it easier to mine that out. So in 1952, somebody who was looking for coal decided to check out the dome. They sank one well into it, kind of on the flank of the dome, not right at the center. And for the first 1,000 feet or so, they saw pretty much what they expected to see, just the usual topsoil, glacial deposits. And then they got down into the kind of ordinary expected Silurian Ordovician Illinois Basin stratigraphic succession. They went through the Maquoketa Shale, the Ordovician Maquoketa Shale, which is expected to be around 200 feet thick at that location. And when they got through that 200 feet, they got to something that looked a little different. It looked kind of like the Maquoketa Shale, but it was a little more carbonate heavy. Wasn't quite the same color, wasn't quite the same texture. So they didn't know what to call it, so they called it abnormally thick Maquoketa Shale. They kept on going through that. It's a 1,200 foot deep hole, and at the very, very bottom of the core, about the bottom 10 feet, they came up with the stuff that you see over here in this picture. They came up with this weird vuggy, sandy dolomite, kind of bleached looking. They didn't really know what to call it. What you expect to find under the Maquoketa Shale is the galena dolomite. And although this doesn't really look classically galena for the most part, they just went ahead and called it a few feet of disturbed galena dolomite, then left it at that. I don't think it turned out to be a fruitful hole for coal, so nothing more was really done with it for a few years. But a few years later, Silco, the Central Illinois Light Company, which is now under Ameren, was looking for a place to build a new gas storage field, and domes are favorable for that. They were doing gravity studies in the area. You know, they knew there was supposed to be a dome there. They did a gravity study to confirm the presence of a dome that was about 4 kilometers, 2.5 miles in diameter. You can see their residual gravity map down in the lower left here. And the town of Glasford, you can see it is fairly close by. It's a very small town. So this is their public land system, township range. These are a mile on each side, these squares. So it seemed promising for a gas storage site. And so they went ahead, and in order to find out more about the well, they sank, find out more about the structure, they sank several more wells into it, into different parts of the dome. This over here is a little map of where all the different wells that they sank were. Peters number 1 is the one that I showed you before. And they also drilled the well called the Cowser number 1 right in the very center of the dome. and they went down 2,700 feet with it, and they cored at least the bottom 1,200 feet completely. And thank goodness they did, because basically my entire project was made possible by them doing that. Oftentimes when people drill a deep hole, they don't pull out intact core because it's pretty expensive to do that, especially if you're starting to go down thousands of feet. Oftentimes they'll just rely on the broken up chips of rock that come back up with the circulating mud from a drill. But they went ahead and they cored the entire thing. And this is what they saw. Again, for about the top 1,100, 1,150 feet, they saw mostly what they expected, except for that weird abnormal Makokata shale they were talking about. But then at about 1,155 feet, they started seeing rock that was completely distorted, destroyed, broken up, torn up, mixed up, and thrown around in all kinds of weird ways that made it really obvious that something very unusual had happened here, that there had been some kind of really big release of energy that had fractured, mixed around, and altered rock. So here we have, so these are all pictures of core. This is whole core. This one's split down the middle to give you a better view of what's inside. They were finding breccias that were full of a wide range of different clast sizes. The top part here is just one really big clast floating in the breccia, but there's a bunch of much smaller ones too. And the pieces within the breccia, a lot of them were not recognizable, either because they were too small or because they'd been altered to some degree. But here and there, they thought they were spotting pieces of formations that were expected to be found much deeper down than, 1,200 feet. This is a little deeper. It shows a breccia dike. So it shows where a big crack, a big fracture opened within the rock. And, the host rock itself looks kind of altered. And then apparently a crack opened and breccia was kind of forced into it, almost like a fluid. Go down a few hundred more feet, down to about 1,776 feet, and they started finding things like this instead of the pretty flat lying layers you would expect to find in this part of Illinois, in most of Illinois. They were finding things that were bucked up at, 45, 60, 75-degree angles to the horizontal, and they were kind of chewed up in all kinds of interesting ways. This is a nice polished slab where you can see there's micro faulting and micro fracturing on this thing. You can see where there's little tiny, you can see these nice sort of darker marker beds, and you can watch how there's all these little displacements. So you can see all kinds of weird little micro faulting motions occurred on here. The bands themselves are a bit of a mystery too, based on the rock that it's formed in, but we'll get back to that later. They kept on going. They came about 2,100 feet down or so. They started seeing formations they recognized a little bit more. They came to stuff that they recognized as the Cambrian Eau Claire Formation, which is very shaly, but it was coming up in pieces. It was coming up in fragments. When you go pull out the core box at the state survey, and you go to this interval, all you find are these big chips of the stuff that are silica-sided on either side. They've got kind of a sheen. It looks like maybe the clay minerals on the outside were altered in some way. And in a couple of places, you can pull out weird stuff like this, where you have these pieces of shale that were apparently like twisted and compressed and folded in probably a couple different directions at once almost, it looks like, just in this complex pressure regime that occurred at the moment of impact. Some of you probably know who Steve Marshak is. He's a structural geologist and recently retired at the University of Illinois. He wrote a whole bunch of intro textbooks. So if you've taken geology classes, you might have read some of his books. He wrote the book on structural geology. I read his books as an undergraduate. So one of the proudest moments of my career as a geologist was taking him to see this core and pulling this out to show him. Steve always can talk your ear off about what he knows everything. So whatever you show him, he can just start talking and tell you exactly what it is. But when I showed him this, he was dead silent. He just stared at it, flabbergasted for like 30 seconds. He'd never seen anything quite like this. So I showed Steve Marshak something he'd never seen before. That was a happy moment in my life. And then, so that's about 2,200 feet. If you keep on going, you'd see the formations you'd expect to see, but they're mixed together in different orders. They're not always where you think. There's alternating intervals of formations kind of intermixed. And then maybe the bottom 30 feet or so, you get down to the Cambrian Mount Simon sandstone, which is considered to be the basal sedimentary unit in the Illinois basin. But when you get to it here in the Cowser Well, it's about 1,000 feet above where it's supposed to be ordinarily based on regional mapping. And the Eau Claire also, when you encounter it for the first time in this well, it's 1,000 feet shallower than it's supposed to be. It's been pushed up 1,000 feet by something. So the people who had to make sense of this, of course, were the Central Illinois Light Company people and also the ISGS people. So in 1963, T.C. Bushback at the Illinois State Geological Survey, there on the left, and then Robert Ryan, a geologist for Silco, published a paper on this thing in the American Association of Petroleum Geologists Bulletin. They called it a crypto-explosive structure, which is their way of saying, we don't know precisely what it is. Clearly something released a huge amount of energy here. We can't say for sure what it is, but our best guess is a meteor impact. In 1963, the study of meteor impact craters was relatively new. They didn't know about that many of them. They were starting to find more around this time, so it was kind of on their minds anyway, I imagine. But so that they had that in mind as an option, but they weren't ready to commit just yet. Their model of what this thing probably looked like is shown here in this diagram from their paper. They pictured it as basically just a big hole in the ground, a big pit full of giant boulders that had been, kicked around by this explosion, whatever it was, and then subsequently buried by intervening geological processes. And that little dome in the middle, they attributed to some kind of tectonic uplift that occurred, in the millions and millions of years after this thing was formed. So they were able to figure out that this probable meteor impact happened probably in the later Ordovician, just based on some inferences. So that's 1963. They published their paper about this thing, and then for a good 50 years after that, 50, 60 years, nothing really happened. No one really looked at it very much. In the mid 1980s, there was a team of people from the state, the Illinois Survey, and also a guy named John McCone from Texas. The study of meteor craters was progressing, and they had worked out ways to sort of decide for certain what was or wasn't really a meteor crater. One of the criteria you can use to say, okay, this definitely formed from a hypervelocity impact of a bolide hitting Earth are these things called shatter cones. This one here is not from Glasford. This is a picture I got online of a very nice shatter cone. But there's these kind of almost like conchoidal fracture things where they're striated, they're kind of curved surfaces, they nest within one another in what's called kind of a horsetail pattern. They're pretty distinctive, and they are thought to only form with a nuclear explosion or a meteor impact. Those are the two things that can make the level of pressure necessary to create these things. So in the mid 80s, John Nelson and Mike Sargent from ISGS and John McCone from Texas went to look at the core we had from Glasford, which is at the ISGS repository, as well as the Des Plaines disturbance core to go look for shatter cones. And they found them. At least they said they found them. And they talked about it a little bit at a meeting, and they wrote up a very brief abstract about it for the meeting saying, hey, we proved it. These are meteor craters. We found shatter cones. And then again, kind of all quiet for a couple decades. And then around 2015, 2016 is where I got involved. I was working on a project that involved kind of surveying all the different places in Illinois where there were major fault zones and like major places where the rocks had been fractured and disturbed. And I happened to be kind of leafing through an older book on Illinois geology, and I read about the Glasford structure. I saw that kind of pit in the ground image. And I from there, I went and I read up a bit more about what we've figured out about impact craters in the meantime. And I realized, in kind of a manner of speaking, um, a large impact crater is sort of a very special, highly localized fault zone, in a manner of speaking. So I took that to my bosses and I said, this is something that no one's really looked at in a good 30 years. No one's looked at it seriously in 50 years. Could I have a little time and a few resources to just spend a little time with this? And I'm fortunate that they said yes. So the first thing I wanted to do was just basically just bring the Glasford structure into the 21st century, because planetary science, the study of impact craters, has advanced enormously since Bushback and Ryan did their paper in 1963. They did good work. They did great work for the time, but we know a lot that they didn't, just based on more and more impact craters being discovered, being studied carefully, modeling being done as far as how these things are formed. One of the first things that jumped out at me, they had modeled that mega breccia pit, that hole in the ground filled with boulders. But at 4 kilometers, 2.5 miles in diameter, based on what I was reading in the literature, an impact structure that size would not be expected to just be a hole in the ground. It would be expected to look like this, something that's called a complex crater, which, yeah, there's a pit, but there's also a central uplift in the middle. There's a big rise in the middle where underlying rock was faulted and pushed up. And that, of course, fit the dome that we knew about at Glasford fairly well. So that was the first thing I wanted to do, was just kind of update the model. As far as why that happens, just a very, very quick primer on how meteor craters form. So when an asteroid comes down and contacts the Earth, you all remember from science class, every action has an equal and opposite reaction. When a large asteroid traveling very fast hits the ground, an enormous amount of pressure, of course, is generated by that impact. It creates a shock wave, which radiates both into the ground, but also back into the asteroid itself. So the actual bolide is pretty much disintegrated, usually. You might find little bits of mineral and certainly some geochemical evidence here and there, but you're not going to find big pieces of meteor because they got obliterated. So the next step is what's called a transient crater forms. You have the rock that was at the impact spot is vaporized, melted, blown up into the air. You get what's called an ejecta plume, which is very, very fine, pulverized, melted stuff going straight up. You get what are called ejecta curtains, which is a little coarser stuff kind of shooting out either side and making ejecta blankets. That goes back to those 46 ejecta deposits I mentioned earlier. You might have molten rock at the bottom. The rock underneath and to some degree around the crater gets fractured and even faulted all the heck. And then once it settles down, if it was a relatively small bolide creating a relatively small transient crater, when it kind of collapses out and becomes the finished product, it's what's called a simple crater, which is what you see over here on the lower right. And that really is just a lot more like kind of your classic hole in the ground you might picture. It's a little more complicated than that. There might be rings around the edges and that kind of thing, but it's more of just the pit. Whereas a complex crater, once you get over about like 2.5, 3 kilometers diameter for an impact crater on Earth, you get a complex crater. And what that means is when all that rock is removed from the impact site, a lot of pressure holding down the underlying rock goes away, and the underlying rock rebounds upwards to fill that space and creates that central uplift in the middle. And that's formed by big pieces of underlying rock being pushed up in mega boulders along faults. Then you also get down faulting along the edge. Depending on the details, you might get a lot of melted rock. You might get a melt pool in the middle, and a lot of interesting stuff going on. So since Glasford was 4 kilometers wide, we expect it to be a complex crater. All right, so when I first tried to get this published, I wrote up a fairly straightforward paper, with some new images of the rocks, some thin sections, some details that I'll get to later, kind of put it in the 21st century context of what impact crater is supposed to be like. And I sent it off for review to Meteoritics and Planetary Science, one of the big journals in this field. And they came back to me and they said, well, this is interesting. There's some good work here. Yeah, this seems like it's probably an impact crater, but you haven't proven it. There's no actual proof here that it's an impact crater. And I was a little shocked by that because, they found shatter cones in the 1980s. Every online database, every textbook I'd ever checked, listing out impact craters included Glasford as a proven impact crater because of those shatter cones. But here's the problem. I mentioned before about how everybody wants to find an impact crater, and nature has lots of ways of making, vaguely circular objects that seem like they could be an impact crater. So planetary scientists have really pinned down a very exact set of criteria for saying, okay, you really do have a crater. Shatter cones is one of them. Something called planar deformation features, which I'll discuss next, is the other thing. But they don't just want you to find them. They want you to document them very thoroughly. It's not enough to say, yeah, we got them, it's cool. They want you to illustrate them, document them, have them in the literature. And the guys who published that stuff in the 1980s didn't do that. So I said, okay, fine. All I have to do is go find those specimens those guys had and take pictures of them and include them in the paper, and we're all good. So I went to look for them in the ISGS holdings, and a very long odyssey began because nobody knew where the heck they were. People had heard of them, but nobody had the slightest idea where to actually find them. People had a few ideas where to look, and they were not there. Spent a long time asking people, and finally someone actually helped us get a hold of John McCone, the guy, one of the lead authors for the study in the 1980s that found the shatter cones. And we finally got in touch with him and said, hey, we need to illustrate those shatter cones. Where are they? And he said, oh, they're gone. They're long gone. They were stolen. Apparently, he committed kind of a no-no. He took the shatter cone specimens back to Texas with him, never gave them back, just put them in a storage unit along with a bunch of other mineral specimens. And apparently, the way he tells it, somebody must have gotten wind that he had a bunch of valuable mineral specimens in this storage unit. So in the dead of night, somebody broke in and made off with everything, shatter cones and all. So they're gone. They're in a ditch somewhere, or possibly they got sold at a mineral show and they're sitting on someone's, shelf, but they were not available.
Have you tried to find it and get them back?
No one has any idea where they are. I mean, if someone bought them, they might not even have known what crater it came from. They might have just been told, here's a shatter cone. So yeah, we have no idea. They're gone. So that put me in kind of a pickle because I wasn't going to be able to get this published if I couldn't find some shatter cones. And I figured, well, they probably went through and took all the good ones. I don't think there's any more to find, but I didn't have much choice. My only option was to just go back and look very, very, very carefully at all that 1,000 feet of core. From the sparse notes they had left, I figured out kind of the general interval in the core where they found the shatter cones. So on my birthday, as a matter of fact, I sat down to look at the core, hoping to find some shatter cones as a birthday present to myself. And lucky me, there was one spot at the broken edge of a core I found. They weren't very big, they weren't terribly well developed, but there were these little cone shapes, curved surfaces, nested striations. They looked shatter cone enough to be convincing to me. So I took some pictures and I sent them back to Meteoritics and Planetary Science. And I was like, are we good now? Are we okay? And they said, those pictures aren't very good. That could be anything. So I got our ISGS photographer to get out his really good cameras, his really high-res cameras. He took a bunch of pictures. He messed with them in Photoshop to kind of stack them to improve the resolution. And we came up with this. We got this really nice clear picture. And I went ahead and did a diagram where I kind of mapped out the boundaries of the cones and where the striations were. And that was enough. They accepted that. So in a sense, I was there. I was actually there for the first one to actually prove to the satisfaction of planetary science that Glasford is really and truly a meteor impact crater. So besides shattered cones, which we now had, the other thing you look for is planar deformation features. And what those are, um, you might have heard the term shocked quartz. Basically, when quartz and some other minerals too, actually, is subjected to really, really high pressures on the order of gigapascals. I'm not a mineralogist. I can't even explain to you exactly how they form, but basically what happens is under those conditions, there's some kind of failure along planes within the quartz grains, and that failure kind of runs parallel to the crystallographic axes of the grain. So when you look at it in cross section and thin section, what you see is looks like a bunch of little lines, bunch of little striations running across the grain. Oftentimes there will be multiple sets of these things in different orientations because again, minerals have multiple crystallographic axes and you can get these PDFs forming along any of them potentially. So before I even knew if we were going to find shattered cones, I figured this would be a good thing to try to look for also. And based on other case studies, I figured that the trough, the annular trough around the central uplift is where stuff tends to collect sometimes. That would be a good place to look. So I went back to that Peters #1 core, to that weird, vuggy, sandy dolomite, took a few thin sections of that. This picture actually didn't come out very well, I'm realizing, but maybe you can sort of see here, we've got this oblong grain in the middle. Maybe you can sort of see how it's really just crisscrossed all over with parallel lines going in a couple of different orientations. And there were lots of grains like this in that sandy dolomite. We just got a fairly small sample with only a few thin sections, and we found, I'd say, a couple dozen grains that had these things on them. Now, the thing about proving these are PDFs, again, nature has different ways of making, linear features on a grain of quartz. To really prove that these are actual PDFs formed by a meteor impact takes special equipment that neither I nor anybody else in my research team had access to or even would have known how to use if we did have it. The most popular way to do it is something called a universal stage, which is something you can mount on a microscope and it rotates and you can use it to confirm that these planar features actually do correspond to crystallographic axes. We didn't have that, so we wound up just in this first paper we published, we wound up just illustrating a bunch of these grains, kind of pointing out the different orientations of all these different sets of maybe PDFs. We even thought we'd found a few examples of something that's called feather features, where you have a PDF or a planar fracture, and then you have little smaller ones kind of spalling off from it in kind of a feather appearance. And so we published this and we said, we didn't have the equipment. We can't prove that these are PDFs, but they look very suggestive. And within the context of having shattered cones, it seems like the best explanation. And lucky us, we published the paper, and not too long after the paper actually came out, I was contacted by a guy named Carl Almark in Sweden, who works at Lund University, which is a big center of meteor crater research. Sweden is actually very rich in meteor craters. And he said, oh, by the way, I've got a universal stage. If you send me some samples, I'd be happy to take a quick look at them and find out if you've really got PDFs. And he did, and in no time flat, he wrote back and said, yeah, these are definitely PDFs. We actually just had a poster at the Lunar and Planetary Science Conference earlier this year where a couple of images from here where it shows how he's kind of highlighted some of the different sets of PDFs and planar fractures in here. The numbers in brackets indicate the crystallographic axis that the different orientations correspond to. He went through and he looked at a whole bunch of grains and sort of tallied up specifics. He actually found two different populations of grains in here. He found some that were smaller and some that were larger, and there were different distributions of PDFs and PDF orientations between the two different populations. So we're still trying to figure out exactly why that is. My best guess is maybe the smaller grains were also rounder, so they probably came from a deeper formation like the St. Peter sandstone is my guess, and maybe something about the conditions of the St. Peter relative to the other substrate changed the distribution, changed how the pressure interacted with the sediment is my best guess. But that's still work in progress. Hopefully that's going to be a paper fairly soon. Okay, so at this point, we had proven to everybody's satisfaction that yes, the Glasford structure really is a meteor crater. What can we say about the meteor itself? Well, at this point, if you go look at a meteor textbook, like the one written by Bevan French, you can find graphs that just map out on a fairly basic level the correspondence between the size of the crater and the expected size of the bolide, in a very general sense. And then you can also connect that to the amount of energy that would have been released. So for a 4-kilometer wide crater, just in sedimentary rock, you would expect the bolide that formed that to be about 200 meters in diameter. And 200 meters, for comparison, if you look, here's a picture of Wrigley Field over here on the right, and the yellow line connects the scoreboard to the press box, and that's about 210 meters. So basically, we had a rock that was about the size of Wrigley Field falling out of the sky onto Illinois. The energy release when this thing hit would have been comparable to about 800 hydrogen bombs going off at once. The total energy released would have been substantially more than the energy released by Mount St. Helens in 1981. And the thing is, the really amazing thing is, this is pretty small by meteor crater standards. I mean, compared to Manson or Chicxulub, this is nothing. Certainly, I would not have wanted to be a trilobite hanging around near Glasford, the Glasford, Illinois area when this thing hit. But there was no extinction associated with this impact or anything like that. It was a relatively local event. Things got back to normal pretty quickly after it happened, probably. Okay. So this thing, as I've already explained, this thing is buried. It's completely buried under over 1,000 feet of sediment. So in order to really say anything about it, we have to about the larger scale structure, we have to look at analogs. I'm hoping that someday I can get the equipment lined up to do a seismic survey of this thing and get a better look at what it really looks like underground. But until then, we kind of have to rely on analogs. So there was a nice paper on the structural geology of impact craters published in 2014 by a guy named Kankman. It shows, so this is kind of a quarter section of a complex impact crater. So it shows the mega blocks in the central uplift that have been pushed up along different kinds of faults. It shows the normal faults dropping down along the crater rim. It shows the annular trough, or whatever you want to call it. I've seen different names for it, in between the rim of the crater and the central uplift, and that's full of different types of material, allochthonous brecciafill, could be some melt, could be a lot of things. And then sometimes you've got slumped crater rim stuff around the edge. So we can guess that Glasford on a broad scale looks kind of like that. Another way to go get a feeling for what it might look like underground is to go just over the border to Indiana, where the Kentland impact structure is found. And that place is great because there's actually a quarry drilled into it. So you can go there and you can really, really see what an impact structure looks like from the inside. So I got to go on a field trip there for GSA when that was in Indianapolis. And you see some really bizarre things there. You see stuff thrown up at weird angles. Like over here on the left, you can see we have Ordinarily flat-lying galena and Macokota. It's tilted up at 45-degree angles, but that's not the most interesting part. The most interesting part is the younger Macokota is over here underneath the older galena. It's not just 45 degrees, it's like flipped over, 135 degrees. Elsewhere in the crater, hopefully you can see the light conditions are a bit harsh, but hopefully you can see a big black wedge, a big black triangle, just sort of driven down into this lighter stuff. That is a gigantic wedge in Macokota, just rammed or maybe pushed, who knows, into galena. And you can see stuff like this all throughout the crater. It's a really, really fascinating place. If you ever get a chance to go there, I highly recommend it. And there's shatter cones all over the place. You can take home shatter cones. But on a finer level, we had that core, and you can do a lot with a single good core. So I mentioned Steve Marshak earlier, the structural geologist. He has been working with a grad student who's actually now at Iowa, Guo Cheng. He's been working on a structural inventory of that big Kauser core that goes right down through the middle of the central uplift. And they've done some really interesting work. They've mapped out all kinds of sort of micro displacements, micro faults, on echelon faults, lots of stuff going on. And of course, a crater like this contains some very, very large scale faults too. That's how you get those very different age rocks being closely juxtaposed, but you can't see that very well in a single core. That's where the seismic data would come in handy if we can ever get it. I showed you a picture of a breccia dike earlier, but these things also have open fractures in them, sometimes filled fractures, very heavy stylolitization in some parts of the core, sometimes connected by fractures. You have these pressure solution seams, which are connected by a fracture here, which is kind of interesting. And in different places in the core, these pressure solution seams can be horizontal, elsewhere they're vertical, or they're at weird angles. It's really interesting. Again, it speaks to just a very complicated pressure regime when the impact hit, because a lot of this stuff just happened, in a split second practically. When an impact crater forms, it happens pretty fast. Something else I've been working on, but it's not very far along. I was able to send some of the Glasford core to the National Energy Technology Laboratory, and they CT scanned it for me. There's a lot I can do with this potentially. It's only just getting started, so all I can do right now really is show you pretty pictures. It also came with XRF data, which basically means that they mapped out the elemental concentrations and distributions within the core while they were at it. But here, we have, this is a picture of one of those breccia cores from higher up in the central uplift, and here's a CT scan of the inside. You can see it's fractured, but you can also see the boundary of where a big clast contacts some of the finer stuff. Here's a piece of core from about 1,457 feet. You can see stylolites, you can see fractures of different kinds, corresponding to some degree, maybe connecting to some degree with the stylolites. And then you can look on the inside, thanks to the CT scan, and kind of see how well the fractures connect up on the inside. Some are kind of discontinuous, some are fairly well connected. And then over here is just an example of, some of the tilted beds and how some of the rocks are a bit distorted inside there. This is from pretty close to the bottom of the core, 2,446 feet depth. Not 100% sure what this is actually, but it's probably Eau Claire, probably one of the more carbonate heavy elements.
Let me know if you need anything. Oh, Summer, you are so beautiful.
Oh. Yeah, they're pretty nice, aren't they? Okay, so one thing that pops up a lot of different places in this core are these black bands, and they were taken to be shale by Bushback and Ryan. Understandably, they look like shale. That's what everyone thought they were. But as we were going through the core again for this most recent project, people started to notice, it wasn't always behaving like shale. It wasn't just in little flat, shaly looking layers. Sometimes it was sort of interlayered in very strange ways with little dolomite layers. Sometimes it was filling fractures. Sometimes it actually formed a matrix in breccia, formed weird irregular lenses. It didn't quite seem like it was always acting the way injected shales would act, which was the Bushback and Ryan model. So some of my collaborators at Texas Tech actually took a sample of, I think this one right here, and threw it under a microscope. And what they found was it's not shale at all. It's actually microcataclysite. When they looked at it under SEM, they found the quote unquote shale bands were full of teeny tiny little jagged rock pieces, micro breccias. So over here, this part labeled white band, that would be the dolomite matrix. And then you have these bands of cataclysite shooting through it. And the SEM also included what's called EDS, which basically, again, it's a way of looking at the minerals inside it. And it found that this stuff here, the microcataclysite, has a lot of sulfide minerals in it. So Steve Marshak's model of this, he calls it impact fracking. His picture is that the heat and pressure of the impact decomposed the carbonate rocks that were impacted, probably producing supercritical CO2. That supercritical CO2 picked up silicate fragments of rock that were created during the explosion, carried them along with it as it was kind of shooting through the cracks that were forming, made the cracks larger. And then this it was carrying these grains along with it, these little tiny breccia pieces. And then when the supercritical CO2 fluid kind of stopped moving, the grains were left behind and they propped open these fractures. So that's why he calls it impact fracking. It's kind of similar to what they do when they, inject proppant, sand grains or something like that, into cracks underground when they're doing, unconventional hydrocarbon production to keep the fractures propped open so you can get more oil or more natural gas. And then the final stage is because the fracture was propped open by these little tiny bits of microcataclysite, subsequently during some kind of hydrothermal flow or something later on, it was able to go through here and sulfide minerals were deposited. So that's his model for how this happened, and it seems fairly plausible to me. Okay. And I guess I haven't mentioned this yet, but yeah, one thing that happens quite commonly at large impacts is that the heat of the impact and the fact that the rock gets fractured and faulted at that spot results in the creation of a hydrothermal system. So you have very hot fluid circulating for a long time after the impact. That can support life sometimes, it can support microorganisms, but it can also be a good way for mineral deposits to form. So that's where the sulfides came from. And you can also sometimes find economic mineral deposits in impact craters related to this kind of thing. Okay, so there you go. Hydrothermal activity. It does tend to seal the fractures over time. It's kind of self-limiting because over time, that hot fluid circulating through carries dissolved things with it, which eventually precipitate out and fill the fractures. If you look at the Cowser core, we definitely see evidence of this happening. We see lots of sort of degraded sulfite minerals, galena, sometimes sort of in, I don't know if you could quite call this a vein, but kind of a band, pyrite, chalcopyrite, things like that. One thing I forgot to mention earlier when I mentioned the gravity mapping is Glasford's a bit unusual because it has what's called a positive gravity anomaly. Usually most impact craters have a negative gravity anomaly, and that's never been clearly explained. One possible reason for that would be that maybe the impact went all the way down to the crystalline basement rock, and then maybe some crystalline basement rock got pushed up in the central uplift, and that's part of why it's reading denser. But based on the standard models of how deep impact disturbance goes for a crater this size, and also based on regional mapping where we think the basement should be in that area, I don't think it should have penetrated the actual crystalline basement. So on some level, I'm holding out hope that maybe there's some kind of mineral deposits in there that we haven't found yet. Maybe that's partially accounting for the gravity signature. I'm not
How
telling
far
you.
is it to the basement there, Charles?
What's that?
How far is it to the basement there?
Oh boy, I'm trying to remember, but it's at least in that part of Illinois, it's at least 4,000, 5,000 feet. I think it's definitely, when I did the math, it seemed like the basement was about 1,000 feet deeper than you would have expected the impact disturbance to reach. So, you know, it's a ways down there.
Okay.
So yeah, I mean, I'm not telling you there are economic mineral deposits there. I'm not telling you to buy amber in stock, but this is something I'm hoping to look into more in the future. Okay, getting into a little more sedimentary geology for any fans of that. One of the other things we did in this project was characterize crater fill. So this happened in the Ordovician. We know that just based on its basic placement in the sedimentary column. And based on about when we think it happened, we would have expected it to be a marine impact. We would have expected Illinois to be underwater at that time in a shallow tropical sea, with the seafloor looking kind of like this Ordovician seafloor diorama from the Burpee Museum in Rockford, you know, crinoids, little nautiloids, the whole 9 yards. And there were very brief references in that 1963 paper to marine fossils being found in the upper part of the structure, which would seem to support that. So we went to look at the crater fill in a bit more detail. So there aren't that many marine impact craters that have been identified, but there's been enough that people have worked out kind of a model of what it looks like in terms of the sedimentary regime when, you know, one of these things forms in the ocean. So of course you have water getting blown out and then it rushes back in. And when it rushes back in, it carries with it, you know, some of the stuff that got ejected from the crater and also some of the other, you know, seafloor sediment that was already there. And there's kind of a succession you expect to see of different kinds of, you know, gravity flows, you know, turbidity flows, debris flows, density flows, all of which are recognizable in different ways based on the texture and sorting and things like that. And there's a certain succession of those worked out that you expect to see in a marine crater. So we went to see if what we actually found in the crater fill sediments fit that. And for this, we had to go back. Okay, so filling in on that a little bit more broadly, the first thing you would expect to see, first as in lowest down in the succession, would be slides and slumps of material coming off of the edges of the crater. Then you would see, so slumps could be indicated by things like soft sediment deformation. Underneath that, there could be just plain old avalanches of large material. You would start to get into mass flows of different kinds, which is basically various kinds of detritus and fluid moving under the influence of gravity. So that could include sand grains, could include fossils, followed by density currents, which are kept in motion by gravity acting on density differences, turbidity currents, things like that. And then once everything quiets down, you would then get back to kind of normal marine fine-grained suspension deposits. But that's kind of after everything has sort of fallen out and calmed down. So going back to that Peters core, which was on the flank, which was more where we would expect to see the crater fill. So we had that, and we had a little bit of core. So going back to the beginning, I'm not sure if you remember, but there was the main Kauser core right through the center of the structure, and then several wells around it. And not all of those wells had core, but a lot of them had cuttings, which are little just bits of rock, but sometimes are enough to at least tell the lithology. And a lot of them had geophysical logs, which tell you something about the type of rock and the density of the rock, that kind of thing. So by putting all of that together for all those different wells around the flank of the central uplift, we were able to draw some generalities. So going now from shallowest to deepest, starting right underneath the Maquoketa Shale, there was that interval that was called the abnormal Maquoketa, which was actually a dolomitic shale. This was interpreted by previous workers as an unusual basal interval of the Maquoketa Shale. Actual age, I would say, is indeterminate. We never perfectly settled on exactly which formation these would correspond to. We interpreted this as kind of transitional from the deeper crater fill units going back up to the regular Maquoketa when things really got back to normal conditions. Underneath that is what we call the dolomite limestone interval. This had a lot of soft sediment deformation, shaly interbeds, trace fossils, a few things going on. We weren't quite sure what they were. There was this kind of stigmatic ribbon over here. We were never quite sure what that was. Some kind of elephant skin looking textures on some bedding surfaces, which might be a place where maybe something slipped, most likely, maybe a motion surface. And then again, soft sediment deformation indicating different kinds of loading. So definitely consistent with some slumping and things like that. This interval is fossiliferous. Now, the Peters core, it's like that wide. So it's not going to be like the Decorah crater. We're not going to be finding big pieces of giant eurypterids in it. What we were finding were things like this. You can tell it's something, you can tell it's segmented. Could be a eurypterid, could be a lot of things. We actually had James Lamsdell, who was the Decorah eurypterid guy, look at it, and he said, probably an arthropod. Beyond that, can't really say too much. But the lucky thing for us, even though we couldn't really identify too many of the fossils, the larger fossils, we found a fair number of these things, which are called graptolites. And for anyone who doesn't know, graptolites, they're totally extinct now. It's a group that's gone, but they were extremely common in the Paleozoic, and they were marine. I think some of them lived on the ocean floor, but a lot of them were planktonic. They floated in the water column, and they had a worldwide distribution. And they had fairly ornate shapes, and they also evolved pretty quickly. So the upshot of all that is they're common enough, they're widespread enough, and they're recognizable enough that paleontologists have been able to work out the succession of different graptolite species over time in quite a bit of detail. And by tying it to known formations, tying it to, say, like ash beds where they have an absolute date, an actual, date in years as opposed to a relative date, they've been able to work out pretty well, which graptolites correspond to which age in Earth's history. So we were very happy to see some graptolites that provided some promise for actually dating this crater fill. Moving down, we got to the sandy dolomite. That's the stuff I mentioned earlier, where the shocked quartz grains with the PDFs were found. It was this bimodal thing. It was unstructured in thin section, kind of a mess. And then we got down to a whole bunch of breccia underneath that. So basically, based on that, I made a composite log of what I thought the succession looked like. So the breccia at the bottom was probably a combination of the actual shattered crater floor, maybe in some cases, and then research deposits carrying breccia. Over that, we had the mass flows that were talked about and the kind of classic succession of marine crater infill described by those other authors. And that's what we call the lower sandy dolomite interval. Above that was the upper sandy dolomite interval, and we interpreted that as density current deposits. And then the stuff over that kind of transitioned into just regular shallow marine crater fill. This thing probably retained a topographic low on the seafloor for a while. And, things lived in there. Based on some of the fossils we were finding, I'm guessing especially on the central uplift in the middle, the top of that was probably close enough to the surface to be within the photic zone. There might have been some things living on there. And we could tie a lot of this pretty well to the geophysical logs that we had. So we became able to recognize the different units and other wells, even where we didn't have cores. So we could sort of trace it across the entire structure. And that's what we did. Here is a geophysical log cross-section for a whole bunch of these wells, kind of showing how the different units are distributed across the structure. Okay, so we had the crater fill pretty well figured out at this point. It's collectively, those different little subintervals add up to a unique sedimentary unit, which is limited to the crater. And the nice thing about discovering a new sedimentary unit is that in principle, you can name it if you want to. The requirements for actually formally naming a new sedimentary unit are fairly elaborate. I haven't had a chance to go through it yet. I'm not even sure if they'll accept a unit that's just limited to a single crater. But just for convenience and for fun, I went ahead and named it informally. The town of Kingston Mines, it was the closest town to the Glasford structure, but did not already have another sedimentary unit of some kind named after it. So I called it the Kingston Mines. And maybe someday I'll get to write it up and make it an official part of geologic nomenclature, but for right now, it's informal. Okay, so going back to those graptolites, because we have those graptolites, we have the potential to date the age of the Kingston Mines member formation, whatever you want to call it. And because it's a marine impact, because a lot of this stuff happened very quickly after impact, a lot of this was slumps and gravity flows that filled it in quite fast, it seems fair to say that the age of these crater fill deposits are a pretty good proxy for the age of the impact, not exact, but close enough on geologic timescale. So I'm not a graptolite guy, but fortunately I knew someone who knew a guy who is familiar with Ordovician graptolites. And we were lucky, usually just one graptolite's not going to do it, but we found just enough specimens that were just intact enough that this guy could look at the overall assemblage and say, to me, that looks like the C. bicornis zone. So if there's any graptolite people out there, do you know the details of what that means? But the upshot of what that meant for me was that particular assemblage of graptolites is expected to be early, late Ordovician in age, Sandbian, about 455 million years old, plus or minus 2 million years. And the interesting thing about that is, around that time period, we have something that's been called the Great Ordovician Meteorite Shower, basically in a period of about 20, 30 million years, roughly 440 to 470 million years ago. There seems to be about an order of magnitude increase in the number of impact structures that we found worldwide relative to what you would normally expect for that same span of geologic time. And it's not just the big kind of macro impact craters. They've also done work where they found that the flux of little micrometeorites from space went up by a couple orders of magnitude during this time period. So something happened then, apparently, that was delivering meteorites to Earth much more often than any other time in the Phanerozoic, practically. Again, depending on who you ask, there's anywhere from 11 to 15 impact structures worldwide, particularly in North America and Scandinavia, that have been dated to this stretch and are therefore potentially part of this Great Ordovician meteorite shower. And there's a paper that just came out, I think literally a couple of days ago. I haven't read it yet, but it was arguing that this event might actually be completely unique in the Phanerozoic. For a while there, they were thinking you know, meteor, well, I guess I need to explain how this formed before I can go too deep into that. But for a while, they were thinking this kind of thing might have been happening a couple times in the Phanerozoic, but new paper argues actually this great Ordovician shower might be the only time it happened. How did it happen? Well, what they think happened was it's been tied to something called the L-chondrite parent body breakup. L-chondrites are a class of meteorite. I can't tell you the exact mineralogy that corresponds to, but that's what they are. And they've all been tied back to the breakup of a parent body, a very large piece of L-chondrite in the main asteroid belt about 468 million years ago. So basically there was some kind of collision, extremely large collision. The parent body was probably something like 200 kilometers wide. It collided with something else that was very large, and it sent L-chondrite pieces shooting out across the entire solar system. And based on the dynamics of how this happened, as I understand it, I can't recall if it's the big pieces or the little pieces that arrived at Earth first. I think it's the big ones, but based on that, there would have been a period of, a good 20, 30 million years based on modeling where these things would be coming at Earth over time, creating and resulting in this much larger concentration of meteor craters of that age than you would expect. And the picture here in the lower left is a little L-chondrite micrometeorite found in Ordovician limestone in a Swedish quarry. So as far as actually tying Glasford to this event, right now, the proposed connection is entirely based on coincidence. We can't prove it. In order to really prove that this is officially part of the Great Ordovician meteor shower, we would have to prove that the object which formed the Glasford crater was an L-chondrite, as opposed to some other kind of meteorite that just coincidentally happened to fall during that 30 million year window. There's ways to do that. Geochemically, sometimes you can actually find little tiny pieces of chromite that can be identified as extraterrestrial. We have a couple of possible leads on that. That guy in Sweden I'm working with, we're working on it. Nothing to report yet, but hopefully someday I'll be able to tell you that yes, we found proof that this is actually part of that big meteor shower. So yeah, the L-chondrite parent body breakup has been described as the largest documented breakup event in the asteroid belt in the past 3 billion years. And there's a paper a couple of years ago that came out which suggested that this didn't just deliver relatively large meteorites that formed big impact craters. It also would have delivered huge amounts of dust, basically, of much smaller matter to the Earth. And so there's a paper by Birger Schmitz and a few other people in 2019, which suggested that this giant cloud of dust arriving on Earth from this event basically caused cooling that resulted in an ice age. And that in turn might have kind of goosed evolution a little bit, sort of jumpstart evolution. I won't go through the whole ecological argument they made for why this would result in a biodiversification event, but the idea was this might have kind of encouraged evolution to innovate a little bit, and therefore this might have been tied to something that's called the Great Ordovician Biodiversification Event, which is when a whole bunch of new different kinds of organisms showed up relatively rapidly on Earth. So potentially then, if all this ties together, there's at least a loose connection between Glasford and an ice age and the history of life on Earth. So it's kind of interesting how it all knits together, potentially at least. Okay, so to summarize, the Glasford structure in Peoria County is a buried complex impact crater formed in a marine setting. It's one of 2 impact craters known from Illinois, although I wouldn't be surprised if there's more yet to be found. Out of about 30 in the United States and 200 worldwide, we have conclusively proven an impact origin at this point via shatter cones and planar deformation features. And biostratigraphic data suggest, do not prove, but suggest a connection to the Great Ordovician meteorite shower, and therefore indirectly to an Ordovician ice age and a major biodiversification event in the history of life on Earth. Okay, I'd like to just, again, I won't read through all this, but I would like to quickly acknowledge the funding agencies that made this possible. A lot of this came from the Department of Energy in one way or another through various grants, as well as a little money from the state of Illinois and the University of Illinois. And with that, I will be happy to take questions if anybody has any.
I have one.
Yeah.
Do you think that the meteor shower caused the Ordovician mass extinction?
Pardon me?
Do you think the meteor showers caused the Ordovician mass extinction?
Well, that was definitely something they looked at one point. I think the current thinking is probably not. I mean, it's complicated. Obviously, paleoecology is complicated. There's definitely been attempts to tie the meteor shower to the mass extinction, but this last paper suggested in the long run, it might actually have helped new species evolve. So basically, it's no one knows for sure. I would say it's a complex question. So,
in terms of the Glasford structure, yes, you do have to prove that the material is L-chondrite, but since the parent body broke up, this stuff has been hitting the Earth. In fact, it's estimated that 1/3 of all the meteorites that come into the Earth are still from that breakup, from that L-chondrite parent body breakup.
oh wow.
Yeah. So the other thing is, I read that paper on the dust causing the ice age. It's cute,
Yeah.
but more importantly are the fragments that came in. There's been a lot of work done correlating the fragments that came in to Baltoscandia especially, and the GOLB, the Great Ordovician Biodiversification Event. And it appears good evidence that shows that multiple smaller impacts can actually foster diversification by niche partitioning.
Right, exactly.
And so more important, I would, from what I've read, it seems that more importantly, about 50,000 years after the collision, in comes this swarm of meteorites and hits the Earth. We found them mainly in Baltoscandia and mainly in the Thorsden crater, but quarry, but they were spread all over. And it does appear that smaller impacts are more likely to partition areas and foster diversification. And that occurred in the Darwinian. And by the time Glasford hit, the actual GOLB was pretty much done, and the diversification was going on. But yeah, I would look for I would say it would be likely that Glasford could be from the L-chondrite, because at that time in the Ordovician, most of the stuff that came in, that's what it was from. And like I said, still today, you get about 1/3 from what I've read of the meteorites are from that L-chondrite parent breakup.
Yeah, and you articulated the ecological niche partitioning argument much better than I did. But yeah, I agree. I think it's pretty likely. And we are still working on some things where we might still be able to prove it. I haven't been able to go into my office or the lab very much over the past year, of course, but there's some samples I want to do more with that seem high in chromium. So maybe we'll take a look at them. And if we're lucky, we'll find some minerals in there that can provide evidence. So we'll see.
Yep.
I have a couple questions for you, Charles.
Yeah, right.
Excellent talk, by the way, and I found it very interesting.
Thank you.
I actually got about a dozen questions on the way through written down here, but I end up crossing them all off because you did a nice job of explaining them before I even had to ask them. But one of the questions I had is, I just missed it. I know you mentioned it, but that core that you were looking at from the crater, was that near the central peak?
The big one, the very first one I showed was on the flank of the central peak. The one that we did the most work with, the Kauser core, yeah, that's like right down the middle.
interesting. And one other thing I was thinking about when you were showing that impact fractured shale, it reminded me a lot of pseudotactylite formation. If you get just a little more pressure, you get fractures and rocks moving against rocks, and the frictional pressure actually melts them. Well, if you're dealing with something like a limestone, and who knows how well indurated it is, maybe it just fractured them rather than actually melding them. So, might think about comparing that to pseudotachylites and seeing if there's something like that.
Yeah, but it's definitely that's been brought up definitely as a possibility by some of the people I've talked to who know more about this than I do. So yeah, that's a good point. That's something we've been meaning to follow up.
I have a question about the age too. You said 455 million years ago. I believe that's kind of like at the earliest or even before the Galena. So it sounded like from your discussion that you went through Maquoketa being maybe the last normal geologic unit that you encountered before you hit the disrupted strata. So where's the Galena?
Right. Well, that's the thing. Yeah. If you look at the paper I wrote about in 2019, there's some kind of back and forth about trying to decide exactly, which formation this would or wouldn't correspond to.
Yeah.
I'm inclined to think probably the impact occurred relatively early in Galena deposition, and then the Kingston mines would be within the Galena. But I've heard others try to tell me that they think it might be more likely to be Platteville age based on those numbers. So
yeah,
it's a little murky, definitely.
Based on those, based on those numbers you gave, it appears, but of course there's plus or minus on all of these dates.
Yeah.
That it is actually before the Dike and the Milberg bentonite, so that would put it into the upper Platteville.
Right.
Again, there's enough uncertainty that it could be either upper Platteville or lower Galena that it occurred.
Yeah, that's kind of what we said in the paper. At some point I'd love to get a really good stratigrapher and or paleontologist in there to think about it a little harder and see if they can help me pin it down better. But I'm not sure it's going to be possible to give a clear answer on that beyond just what you just said. Yeah.
Also since the Iowa survey was good enough to train you to love impact structures.
Exactly. Yeah. Exactly.
I'm sure you realize that the Decorah structure is considered to be one of those Ordovician impact structures also. But I don't know if you were aware, but we looked at some of the crater fill at Decorah and compared it to some of what should be crater fill at the Rock Elm structure in Wisconsin, and similar conodonts. So I think that might be a third one in this region.
Oh, interesting. No, I didn't know that part. Yeah, I definitely I meant to mention the Decorah age. So yeah. I know there's somebody arguing with you guys in print about that, but I'm going to go with your date.
That Decorah impact is pre-Cambrian, isn't it? Is that in the Dariulian?
No, the Decorah one. I'm sorry. Go ahead, Charles.
No, you can answer it better than I can.
Well, I was just going to say that in Decorah impact structure, we have a normal stratigraphic sequence right through the St. Peter. And then we go into what was apparently a disconformity interval. And we find the shale that was the crater fill shale there mixed with some St. Peter grains. And then we're into the crater fill. So we think it probably hit, somewhere just prior to the St. Peter transgression.
Did you find any Glenwood mixed in there?
No. We don't have enough. Like I said, stratigraphically, St. Peter's the uppermost thing that we can really identify. Beyond that, I don't know. It's very confusing stratigraphy. We had a drill hole put down right in the smack center of that thing where there's a quarry. Unrelated to the impact, but probably more related to being close to Decorah. But anyway, they drilled a core smack dab through the center of that looking for water, because there's a weird water anomaly in that area because the crater disrupted the aquifers. And that core apparently hit normal stratigraphic section below the disturbed materials in the lowermost Ordovician, which is way, way shallow for an impact structure that
Yeah.
size.
Yeah.
So that it's really confusing stratigraphy. I wish we had somebody who really spent some time working on it.
Yeah, that's bizarre.
Should we see some particular deposit elsewhere in the Galena or Platteville as a result of this?
It's possible, yeah. That's one thing I've thought about. I've glanced quickly at a couple of cores from that immediate area that got to the Galena. I didn't see any obvious signs of, any related deposits, but we don't actually have a whole lot of core material, particularly close to Glasford, that gets down to the Galena. So, and I'm not sure how far from the impact spot you would expect material to travel from an impact that size. So short answer, yes, I'm sure if you looked in the right place, you'd find something. It's just a question of how far away you'd have to go and will anyone ever core there, basically. But yeah, at
And
least,
would there have been a tsunami?
yeah, I would think so. Yeah, certainly it was big enough for that. But yeah, I'm trying to think. The core I looked at was really only a few miles away from Glasford, and it didn't get down to the Platteville. So again, depending on exactly how old the impact was, maybe I might or might not have seen the interval that would contain, any impact deposits, but I didn't see anything obvious in the Galena. So who's to say?
An obvious question. How much material was ejected from this site and how much area would be covered by debris?
Oh boy, that is an obvious question, but I've never thought to actually calculate it. So it's so the thing is, it's 4 kilometers in diameter, and as far as the actual depth of the annular trough, we never quite got to the bottom of the actual trough, but we're not sure if we did. We might have just sort of scraped it. So it's hard to say how deep the trough was, and therefore it's hard to say what the volume of sediments, of rock ejected from that trough would have been. It was possibly, 300 feet deep at least. And the other complicating factor is there might have been post-tectonic deformation of the structure itself, like post impact tectonic deformation of the structure itself, which can kind of distort it. So really getting a good handle on the exact size of the pit that was left is a little tricky, and you'd really need to do that. But I'm sure you could do a coarse estimate of how much material was ejected if you just kind of did some back of the envelope calculations, but I haven't done that yet.
We know, Charles, if you think about Barringer crater, meteor crater in Arizona, your crater would have been about twice the diameter. And if you think about the debris that's thrown out of that crater, you're going to get a ballpark guess for what's going on.
Right. It's a good point. Yeah.
How does this compare to something like the thing that happened in Yucatan?
A lot smaller. Yeah, much smaller. No global effect of any kind, probably. More of a,
Okay.
not trivial, but a local event. I can't recall offhand how big that crater is, but I want to say maybe 100 miles. Ray, does that sound right?
Yeah, that's about right. It's huge. No comparison.
Don, if you don't mind, I'm going to mute you. We're getting an echo.
I'll go ahead and turn it off.
Okay, thank you.
I'm just seeing that I talked a lot longer than I expected to. So,
That was great.
Good.
Any other questions? That being the case, I'm going to stop recording and
I had a question. Is there any evidence, since there was the tidal wave and everything else, is there any evidence that can be found in the fossil records further away from the impact?
Potentially, yeah. I mean, I haven't found any, but the core sampling in that area at that depth is pretty sparse. So it'd just be a matter of, taking a core in the right place and just happening to find it. But yeah, I wouldn't be surprised if you drilled in the right place, you'd find some kind of indication of what happened, away from the structure. But I haven't seen it personally, though.
Thank you.
Charles, a little question. Is there a possibility that you could write up a little summary and a couple of slides to put in our ESCONI newsletter?
Oh, sure. Yeah, I can do that.
I'll ask Dave to give me an email address and I'll send you a note.
Okay, sounds good.
Good, thank you.
Yeah, happy to.
Thank you. I enjoyed it very much.
Great, good. Thank you for listening.
Well, Charles, if there's any way I can help you out, I find this stuff very interesting and maybe retired, but I still keep up on it pretty well. So I'd love to talk with you about it.
Okay, yeah, fantastic. I will definitely bear that in mind. Yeah, just if we ever start actually going to GSA.
Get a hold of me through the Iowa department.
What's that?
You can get a hold of me through the Iowa department.
Right. Well, if we ever start going to GSA again in person, maybe I can just, catch you when we can get a beer and talk about it.
I just want to say thank you very much, Charles. It was a great talk.
Thank you.
Thank you.
Thank you.
Thank you for hosting me.
Thank you, Charles.